Okay. Good afternoon, everyone. I welcome each one of you, and thank you for joining our monthly Tracer webinar series. So my name is Jean-Michel Tin, and I serve as a cybersecurity coordinator for the for Transportation, Cybersecurity and Resiliency, better known as Tracer. For those who join us today for the first time, Tracer is the U.S. Department of Transportation funded National University Transportation Center, led by Clemson University in collaboration with 9 prestigious institutions across the nation. The director of the center is Dr. Ronnie Chaudhary. It is now my pleasure to leave the floor to Dr. Ronnie Chaudhary to begin today's session.
Thank you, John. So it's my pleasure to introduce Dr. Sagar Dasgupta. So he will talk about the GNSS security. The title specifically is the Cybersecurity of Integrated Autonomous Navigation, Vulnerabilities, Detection, and Resilience. Here's a short bio for Dr. Dasgupta. He is a postdoctoral fellow at the University of Alabama. His research focuses on advancing safe, secure, and resilient transportation systems. Specifically, his interests lie in the cybersecurity of integrated autonomous navigation systems and CV2X communication, transportation digital twins, and work zone safety. Dr. Dasgupta is a member of the Institute of Navigation, or IL. It's my pleasure to now, Shagor, to introduce your talk. We are looking forward to learning from you and hearing from you. Thank you.
Thank you so much, Dr. Chaudhary, for the introduction, and good afternoon, everyone. I am Sagar Dasgupta, and I do research on a cybersecurity aspect of transportation cyber physical systems. And today I will be talking about the cybersecurity of integrated navigation systems for the autonomous vehicle. We will talk about its vulnerability, how we can detect the vulnerabilities or attack, and how we can achieve resilience in navigation. So, couple of years back, people are always confused. Okay, we are talking about autonomous vehicles, but you know, when it will be reality that there will be enough autonomous vehicles around us so that we can say, okay, this technology is viable. Now you can see Tesla is using their robotaxi application, and the Tesla owners are getting the delivery of their vehicle without any driver. So now this autonomous vehicle has become a reality. But there is always a question of cybersecurity, and this is a clip from a movie, so it's not real, but we need to really think about, is this possible? So we need to really see that, like, if those Teslas were getting delivered and they become rogue and uh, doing the things in the fiction that we can see right now, what will be the end? So you can see it can totally destroy our transportation system. So that's where the talk starts. So I will be trying to introduce the navigation system for the autonomous vehicles, how it works, and what are the vulnerabilities. And if we look at the current landscape of AVs from level 2 to 4, where the level 5 is the highest, where there will be like no supervision from anyone at any point. But we have already reached level 4. The Waymo has level 4, and Waymo has their fleets running in San Francisco, Los Angeles, Texas, Austin, Georgia, Atlanta, Arizona, Phoenix. So these vehicles are there. Now the question is, we have achieved to get this technology working. They're running in our public road, and safety and security is one of the like prime important things, so that we need to really make sure that these vehicles are safe. So before going into the vulnerability, let's look at the components. So if we look at the components, we can divide into like two types: the hardwares and the software. In hardware, we have two types of sensors. We can say one is like exteroceptic sensors, those who get us the environmental knowledge, like LiDAR, camera, radar, and there's also proprioceptive sensors, which give us the like state of the vehicle, like the location using the GNSS, or You have the acceleration or the orientation using the IMU. On top of that, you will have hardware, the CPU, GPUs, ECUs, because these days, these vehicles, autonomous vehicles, are basically software-defined vehicle. We have sensors, we have software, that's how they work. And obviously, there will be actuators, mechanical actuators like steering system, braking system. On top of this hardware components, we have the software stack. So from the sensors, we have to take care of the noise and synchronize it. So we have the pre-processing modules, perception layer, localization layer, prediction layer, planning layer, decision-making layer, and the control layer. So here we can see a very, it's a generalized framework because in different vehicles, they can use different types of sensors and different types of sensor fusion level. So this is kind of a representation how an autonomous vehicle when navigating, because the main purpose of an autonomous vehicle is going from point A to B. So the navigation, how it will work. So we were talking about the stacks. So if we start from the sensors, um, so they're like GNSS or global positioning, IMU, wheel encoder, LiDAR, radar, camera. So in the sensing and pre-processing, we first calibrate the sensor data. We do the time stamping, time synchronization, and also noise filtering. Then there will be a localization and state estimation. So normally when we talk about navigation, we mainly focus on the stack or the localization and state estimation. So what it does is basically it takes data from all the sensors. So for Tesla, they don't use LiDAR, but they use IMU, HD map, camera, and they localize the vehicle where the vehicle is using sensor fusion algorithms. The most common fusion algorithms are like Kalman filter or extended Kalman filter. Based on that, you get the state of the vehicle. So when I say state, that is basically its lat long or its location in the global frame. On the other hand, all the perception sensors like the LiDAR, radar, camera, they also work there, and they have the perception stack is there, which also use sensor fusion, and it creates a structured world model. From this perception and also localization stack, it's also connected with the map interface. So whenever you are navigating, you can see a map and your location is on that map. So what that map does is it creates all the elements and express in the vehicle coordinate system, the single coordinate system. So when you need to navigate, you need to take control or you do the actuation, but based on what you will do. So you will know your location based on the localization and state estimation, and you will know the location of other objects, moving or fixed. So there may be pedestrians, there may be like other vehicles, and also there may be like static objects. So you predict the behavior of the moving objects, and then in the probabilistic future, you get the trajectories of surrounding agents. So that agent may be a pedestrian, that agent may be another vehicle. So you know where you are, what things are around you, and also you predict their future trajectories. And based on that, you do the planning. So first the route planning. So when you know your destination, so it's kind of decided which roads you need to use, but also which lane you'll have to use for the navigation. So you have to do the route planning as well as the motion planning. So when you know what actuation you need to do, then you go for the actuation or control. That's by the vehicle dynamics control or low level actuation control. So this navigation system works from sensing to control. So this is how the navigation stack works. So here things will shift. So we have been talking about how the system works. Now about how we can manipulate it. Again, whenever this is the philosophy I have seen with most of the like cybersecurity experts, and I also believe on that, that if you're working on cybersecurity, you need to really think from the hacker's perspective. The reason is when you know how to manipulate the system, then you know how to put a gate there. Whenever we talk about cybersecurity for autonomous vehicle, we can think about, okay, there's a single hack or something. It's not. It's a clump of software which has algorithms it needs updates, and also sensors. So the attack surface is pretty much distributed and huge. So it starts from the perception sensors, the camera, lidar, radar, ultrasonics. All of them are vulnerable to different types of attacks. The in-vehicle network. So as there are multiple sensors and also computing units that talk with each other, if that is kind of compromised, then the vehicle will act very unsafely. So this CAN bus, that's which is used these days with new cars too, even if it's not autonomous. But now the industry is shifting to automotive Ethernet. So if someone can get into that like communication system, then it can kind of control the vehicle. The localization module, the GNSS, because GNSS or GPS, this is out like the signal is coming from outside. So basically, it's vulnerable. Anything coming from outside. The IMU can be corrupted using if you can get access to the canvas maps. So anything you update. So map, if you are updating map, and if kind of like you updated wrong map, so map is also part of the like vulnerable attack surface. If you go to the driving stack, so whenever you update any do any update in the system and the weight, because all of the sensor fusion planning control, many of them uses like AI and things. So whenever you update that model over there update, and that includes, if that includes malware, that's another attack surface. Connectivity again. So this BSM, map, or SPAT, these are messages in the vehicle to everything connection. If those messages are wrong, then the vehicle will take like wrong decision. Mobile apps, cloud apps. So even for the current vehicles and infotainment systems, or the connection with other APIs has become always vulnerable. So whenever more connectivity is there, you are riding a robotaxi and you want to play your music or connect your phone with that vehicle, that again opens up a new attack surface. And the physical layer, if any adversaries, they are creating like they are making chips and they put some malware in that when they're manufacturing it, that's another attack surface. So right now the whole vehicle has become an attack surface. So that vulnerability is there, the vehicle is out there. So we need to be very cautious about how we go further, so that the so day by day, as people are getting more accustomed with autonomous vehicle, if vulnerability cases are arising and they're like actors or hackers doing something wrong, it you will make the development or acceptance of the autonomous vehicle systems, uh, it will jeopardize it. So we have to be very cautious about it. Now, in the whole talk, I will be covering four things. One is the navigation software stack vulnerability analysis. I will show some examples too. Then the pen testing on consumer grade localization module. So that will be the localization and state estimation module. That is part of threat modeling. Then the GNSS spoofing and detection using particle filter, that's part of the detection. And for the resilience, I will also talk about how we can navigate an autonomous vehicle when there is no GNSS. So GNSS is one of the like most important input for the global localization and positioning. So navigating in GNSS generated environment, that's part of the resilience. So let's start with this hybrid security vulnerability triage approach for autonomous vehicle software systems. So this is kind of the framework we are working on, where if you look at any software on the market, so it may be a web-based API, anything, the first thing is whenever a software developer is developing a software, they try static analyzer to analyze the code, the whole code base, to see what are the vulnerabilities are there. But the thing is, so the autonomous vehicle software source code or software stack, it's like it's millions lines of codes. So if you run a static analyzer, it will give you hundreds of thousands of the vulnerabilities or warnings. And in most of the time, all those warnings are not uh, like feasible for attackers to use. So it might happen that when in the run at the runtime, none of those lines will be like hit. So we were thinking, okay, static analyzing is part of the industry standards, so we'll do that. But on top of that, we need to really figure out that which of these warnings or vulnerabilities are really real and they're usable by the hackers. So first thing is to run the static analyzer and get the vulnerable file, function, and line of line from the like software source code. And after getting that, we use LLM, because one thing is like static analyzing and there is like dynamic analyzing. So what we want to do first, we want to have the static analyzing result, and then we feed the LLM with the software source code and the result from the static analyzer. Then we will generate the LLM guided fuzz harness. Fuzz harness are basically they are test codes. So it has a template. So whenever there is a like static analyzer will, based on the rules and whichever static analyzer you choose, it will come up with some CWAs. Those are basically tell you what type of vulnerability in that line can happen. And based on that, you can test that function where that line is there and with some different inputs to check how it works, if it's like reachable or not. So when you generate the like code for fuzz harness, so it will have the harness template. The harness template will tell which function to call, the input structure. So what the like structure of the inputs for that function, preconditions, and seed values. Seed values are basically initial values that you will try with. So if you start doing that for like by yourself, because there will be like hundreds and thousands of CWVs you will get from the static analyzer, and you start writing the like test code or like the fuzz harness, it's a tedious job. So we want to do it using the LLM that will create the fuzz harness. So then from the fuzz harness, we compile the fuzz target. So the fuzz target is basically it's an executable code. What happens that in the fast target we can hammer it with different inputs and see what happens. So what we do, we execute the generated harness and we check the code. Like there are many matrices you can check, but we decided we go with the code coverage matrix, sanitizer feedback, and detected crashes. So another thing is you have this fast target, and we are trying with different types of inputs or fuzzing, that how the code works. The code coverage matrix will give us which lines of the codes were hit when the function ran. So we will know that the vulnerability is reachable or not. Sanitizer feedback, we will see if there like some dependencies were there that was checked or not, or detected crashes, or if there is like the any type of crash happen when it was trying to run the code. So when we will know that out of maybe say 100 of static analyzer warnings, we figured out that out of that maybe 70 lines or CWs can be exploitable, then we go for the vulnerability reachability. So the static analyzer and dynamic analyzer, these are generic analyzers. So it's common for everything. But when we look at the AV system, we also need to see that the attack surface, one, what will be the way that the type part of the code can be like reached. So we will try to map the dynamic coverage to static findings and also classify the vulnerabilities. So reachable, unreachable, or partially reachable. And based on that, we will have a prioritized security weakness. So based on the reachability, that's one that we get from the classification. Safety critical relevance. So in which part of the function, in where that vulnerability is, and how it can impact the autonomous vehicle decision making. So based on that, we will get safety critical relevance and also the code matrices. Based on that, we will rank the vulnerabilities like from priority 1 to 5. Priority 1 means like the highest priority, and 5 is like the lowest priority. The report actionable results. So based on all this analysis, we can have a summary of reachable vulnerabilities, evidence, and suggestion for the priorities. Like, so the whole thing is whenever and it's like software developer will write a code for autonomous system stack, they should know how that can be vulnerable and they can correct that from the very beginning. So to test it, because I want to show some results too. So we don't have access to any commercial grade AV software stack. So these are 3 open source software stacks. From there, we chose the Autoware. So this is the mostly used in the academic research, and it has all the like the whole AV pipeline from perception to control. So we use this open source software stack, and we try to check the static analyzer and the dynamic analyzer how they work. So you can see that it has got all the components from sensing to perception, planning, control, localization. So we have the whole pipeline there. So this is the result from the static analysis. So we use the code QL. So here they're rule based because they check for the rule, and based on that they figure out some CWVs and the CWV name and how many instances. For an example, so for this rule, this one, so it says that like it looks for the C++ code where 2 integer values are multiplied and the result is then cast to a larger type, so like long type. So the risk is that the overflow can occur before the cast happens. So this is the rule. Based on that, they had got the CWS on the Autoware software stack. So what the CW means, the common weakness enumeration. So CWE 190. So that stands for the integer overflow or wraparound. So what happens? So it means that the computed value can exceed the range that the integer type can represent. So when that happens, the value silently wraps around to an incorrect number. So now you know this can happen for 201 instances or 201 lines in the whole Autoware code base. So which is like CodeQL found 201 separate locations in the Autoware code base. It doesn't mean that there are like 201 exploitable bugs, but it means that like there are 201 places where this can happen. So that we can look into it further. So this is what we get from the static analysis. In the dynamic analysis, so we use the source code, the whole Autoware source code. We use the static analyzer result, the vulnerable column and lines that we got from the static analyzer. And we also put the system prompt to LLM. Here we use Claude. And then the LLM created the harness, the fuzzing harness, the mock objectives, and corpus. Corpus is basically the initial values for the input for this fuzzing target. So using that, we create the fuzzing target, and this is the AFL++ binary executable file format that we use for the fuzzing target. AFL stands for American Fuzz Log. And from there, we do the fuzzing execution. That means we isolate that function where the vulnerability might be present based on the static analyzer, and then we see that that code is reachable or not. So if we look at the localization module, so if you for this one, there were like these multiple CWs were there in the line 464 and the column 37. It was reachable, but not all of them were reachable. If you look at this one, so it's also inside the localization in the LiDAR marker localization, it's not reachable. So this CWs for this line and column number, we don't need to be worried about. So we need to do it for the whole software stack, and then we will figure out that by doing the dynamic analysis, we can lower down the vulnerability, those are reachable. So that is basically looking into the software stack. Now, most of my work is around the GNSS system. So we try to look into how the GNSS system can be impacted by spoofing. And we till now we were just looking at GNSS receiver or GPS receivers, but this time we tried to spoof a integrated system which has got the IMU and the GNSS. So I'm talking a lot about GNSS, GPS, just to introduce it here. That the GNSS stands for Global Navigation Satellite System, and the GPS stands for Global Positioning System. And this is the type of GNSS that the US own. So these are basically constellation of satellites which are sending their location and the time. And whenever we receive that location from multiple satellites, we can localize ourselves in the global coordinate system. So other countries also have their own GNSS system, like the China has got Baidu, Russia has got GLONASS, European Union has got Galileo, and all of our missile systems, defense systems, they all use the GPS for pinpoint positioning and target. So this is one of of national interest and security concern. So this GPS we are talking about, GPS. This is the US GNSS. This is this much important, but is it safe? It is not, because there are interferences there. And definitely you can look into the war torn zones where they're like war zones. They're like it's already there. But when the autonomous vehicles will be like roaming around your neighborhood and someone wants to uh, try to jam it or spoof it, these jammers or spoofers can also happen here. So it's not safe. So we have to work on that. So how this spoofing attack might look like is just an example. If you see the green one, that's the actual car, and the red one is what the GPS is seeing or perceiving. So I did that experiment. I was just driving that car. If you see, I'm just trying to take a right turn, and here from this point on, I am seeing in my GPS that is taking a left turn. And whenever I talk about an integrated navigation system, what I meant, because one is the like navigation stack, and there is we are right now only talking about the localization and state estimation, and you can use multiple sensors there. But right now, the most commonly used is like the INS filter using GNSS and IMU. So this is one of kind of like the example where you have this GNSS antenna. This is the GNSS receiver. The RF signal is coming in the signal tracking. Now it's tracking the signal for multiple satellites. From there, we get the pseudo range and carrier phase. Pseudo range is basically the distance from the receiver to the like satellite, and the carrier phase is the phase of the carrier wave when it was detected by the receiver. So from signal tracking, we use the positioning algorithms, and we get the position and velocity, both of them based on GNSS. On the other hand, we also use IMU, because IMU give us two rates. One is like the change of angle, it gives us the orientation, and also change of the velocity. So we put these two together in INS filter, and we get the position, velocity, and attitude. So this is an integrated system. It's not only GPS, it's also using the IMU. So we get a better result out of it. And normally these systems are used. So we are trying to see if we try to spoof this GNSS system, means spoofing this antenna, how this position, velocity, and attitude changes. For that, this is our experimental setup. So we are like kind of blessed to have a like state-of-the-art GPS simulator, the GSS 9000. So it can simulate exactly GPS-like signals from the satellites. So it's indoor, but all of our experiments are done outdoor. So what we did, we created the signal based on the trajectory, and then we use a software-defined radio to transmit it. Now the thing is, you cannot just transmit fake GPS signal because like it's prohibited. So what we did, we used this laptop and software-defined radio. We connected it with a coax switch, and this is the GNSS plus IMU. solution enclosure we have, and this is like one of the like top graded. It has tactical grade IMU. So this is how it's connected. Now the thing is, we need two things. One is like we also need how that integrated system is performing, and we also need to know what is the ground truth, exactly where the vehicle is. So we have two receivers basically. So this uBlocks receiver is not affected by the spoof signal, but this GNSS IMU receiver is affected by the spoof signal. The antenna is sending data in both cases. So when we start our experiment, the both the GNSS receivers are getting the actual GNSS data signal, but at some point, what we do, we just cut off the actual one and we feed the spoof one. So that's how we introduce the spoofing. So it's just exactly how it should happen in the real world. So this is the experiment we did. It was done on Thanksgiving evening. Just say, yeah. So the green one is the ground truth. That means it's exactly getting the GNSS signals. It's not affected, it's not spoofed. The black one, if you look here, this is the spoof trajectory we gave to the simulator and it created that signal. If you see when we are going straight, and we tried to make sure that we know the average velocity of this road, and this is just beside our office. So how we simulated that that should really mimic someone is really driving in this road. So till here you see there's very less deflection. It's going really good, but when there's a turning is there, that means the IMU is now giving some different orientation. So now the spoofed route, the red, that is the output from our Novotel IMU plus GNSS solution. It is not following the green or black. So that is the effect we get, that it got confused. So we successfully spoofed it. Now the thing is we want to quantify it. So we want to do more experiment and see how it works. So the pen testing has been done in real life. And this is while we were just trying to do the experiments, this is what we figured out is this is my car when we were in front. You can see that we are in front of the building. So this is our office basically. And there is a shed. So normally where there is a shed, there is no GPS signals. So this is the like Garmin I have in my car. What was happening, we were doing the experiments and there was no transmitter, but still from the cable, I guess some signal was out there. And though I am still here, standing still, it's showing some velocity. The vehicle moved. So that means uh, this we can really spoof tactical grade IMU, GPS, and also we can spoof this type of like Garmin. This is 76 Drive Smart EX. So it has very big antenna. So we can also spoof this type of navigation systems too. Just think you are in a like news place and this is happening with you. So this attack model really worked for us. So now we know how to do these attacks. So the next thing is the detection. So we need to really figure out how to detect it. So here we have took a path to use the particle filters, because if you just go with the detection methods are receiver based, so there will be signal distortion, but you will not get all the information. For pseudo range, double and triple differences, you need multiple receivers. For Doppler inconsistency, this is very much sensitive and not reliable. So what we went for was going with the particle filter. What happens in the particle filter is we get the information from the satellites in the for the initialization, and then we have a distribution of particles, means the distribution location, possible location, and we propagate it based on the IMU values. So this is like the clean pseudo ranges, and is the distribution of local obtained using particle filter. And if someone wants to spoof me, the spoof location should be outside the distribution of the particle filter. And based on that, we can really detect the vehicle is like GPS is spoofed or not. So this is the detection concept. Here you see this is the particle filter. So we initialize with the origin with XYZ set. Then we do the particle generation. So these particles are basically location, possible location of the vehicle. Then the particle is propagated. So the particle is propagated means in time t minus 1, we had a distribution of where the vehicle should be. Then at t, there should be some movement of the vehicle. And from the IMU sensors, basically the accelerometer and the gyroscope, we calculate the INS aiding velocity information. So velocity with the direction. And based on that, the particles propagated means moved for t where the particles should be. Then there is the particle zero range simulation. So we are connected to the GPS receiver. We are getting the ephemeris. The ephemeris are used to calculate the location of the satellites, and there are some correction factors because that's why they are called pseudo ranges, because there's multiple errors that we need to take care of. Then we get this particle pseudo range simulation. So then we can compare the GNSS receiver based ones and our particle propagation based one. We can reweight and resample the particles based on the pseudo range observation. And this is happening when there is no spoofing. So with time, our particle will propagate. So while propagation, there might be some errors, and we use the GNSS receiver, its pseudo range, and we reweight and resample the particles so that they are always, when they're moving in the correct direction. But where is the detection part? The detection part is, so where there's the simulated range generation that we were getting from ephemeris and all the particle distribution. Also, we are getting the pseudo range, corrected pseudo range for GNSS receiver. We check these two. So we check, and then based on a Z score based outlier detection, that our simulated particles and the particles, those are based on the GNSS, they are matching or not. So we created an empirical threshold, and if the difference is more than the threshold, spoofing is detected. So that means we have the GPS receiver output and we have the particle filter output. We check both of them, compare them, and based on that, we can say spoofed or not. So we also did the experiment with our GNSS simulator. These are the scenario definition where we put the motion trajectory, the aiding parameters, then we put the satellite parameters in terms of time, where the satellites would be, and how many antennas we are using, what type of antennas we are using. From there, we log the vehicle motion data, INS data, and also the receiver data, because there is one is like the spoofer, which is spoofer is sending, and there is the receiver that is receiving, and we do the post-processing with the MATLAB. So these are the parameters. The simulation was this simulation is the spoof signal, 300 seconds, and velocity we put 10 miles per hour, meter per second. Then GNSS constellation is basically the GPS one. We use L1, and this is the result. If you look here, so the green one is the particle filter estimation, and the blue one is the unspoofed GPS location. So this is the starting point, and right now I am sitting here. So this is our building. So the experiment started here, and you can see how good the particle filter is mimicking or matching with the unspoofed GPS location. So at this intersection, we introduced the spoof signal, which is basically created based on the simulator. And you see here that the particle filter estimation didn't deviate. The reason is, whenever there was an attack, it detected and then it stopped the correction, because we showed that we are correcting the particle filter here, but we are doing the correction, right? But whenever there is an attack detected, we stop that correction. So though the simulator is the like this spoof signal is there, the red line, but still the particle filter is showing exactly where the vehicle is. So if we look at the error in terms of north and east, so this is the 0 point where the spoofing was introduced, and you can see it just gone just down. It's basically it was not affected by it because it was detected at that point and it stopped correcting, and but still the particle filter were on the way, and the It's like less than 10 meters, and it's a pretty good result for us, so that we can use the particle filter for detection, as well as whenever we don't have GPS for some point, because we did it for 150 seconds after that spoofing occurs. How long it can hold that correct like accuracy, that's one thing we need to see, but we can at least go for 150 seconds without the GPS in the correct path. And this is the detection performance. You can see it detected around 0, and after that the detection is 0. The reason is it's not at all looking into the GPS GPS input anymore. So after detection, it gets back to only working on giving you the location based on the particle filter. Okay, so this part is kind of the resilient part and the last part of this talk. So here, what we are doing, okay, GNSS is compromised, and it's that signal is coming from outside. So if we can detect something, let's cut off the GNSS and let's see how we can navigate on the like urban areas even there is no GNSS. So normally, if you want to see the solutions available whenever there is a GPS denied environment, they're like 3D map, LTE, cellular, 5G. These three comes in the same category. Then inertial sensors, just only the IMU, or using pseudolights. The problem is all of these like 3G, LTE, 5G, pseudolight, cellular, all are external signals, so they will have the same problem. 3D map is really costly, and the updates, if there is something wrong with the updates, you are gone. And inertial, it cannot work alone. It needs the GPS correction because it accumulates error with time. So let's see how we can work without all those things. So this is the full framework. So it has got two stages. One is the localization of shift from look time t to t plus 1, and also a correction part. So we will divide it into two and look into it how it will work. So the first strategy is, okay, whenever there is the GNSS, we will use it. When there is not, we will not use it. So what are the other sensors we already have inside the vehicle? We have this gyroscope, that's part of IMU. We have this accelerometer, and we have this speedometer. So you can use odometer to get the speed. You can use the wheel encoder. Wheel encoder is the like best sensor to get the correct velocity. So we will use gyroscope, accelerometer, and speedometer, and we will predict so how far the vehicle should go by the next time step. So we use two methods. One is the LSTM, which is RNN type long short-term memory model. Another is like the Kalman filter. That's used everywhere. So what happens when you are starting the route, your origin and destination is given, it creates the shortest route. And from the shortest route, we extract all the lat-long because we want to update the location in the global level. So we update the lat-long based on the distance travel prediction. So using LSTM and Kalman filter. Then we feed it to the AV localization. So we know the previous lat-long location, and we know how far it has moved, and we know all the lat-longs along the route. So we update that lat-long. Now here is the thing, zero velocity. So sometimes what happens, the vehicle is stopped, but it is showing some velocity, some random numbers. So we have to check that. So if the vehicle is stopped, because based on the sensor you have, you can check like how it behaves. You fix it based on the threshold. If stop, you don't update the location. If it's not stopped, you update the location, and it goes to navigation system. As I already talked about, the IMU, like gyroscope, accelerometer, they accumulate error with time. So along with strategy one, we have to have a strategy two, correct it. So let's look into the like this is the structure of the LSTM. It's a very nominal, two hidden layers and one dense layer. And you can see the training. The training loss is like these are flat, so means it's a generalized model. And also this is the Kalman filter. We just use the IMU values to estimate and the how far it should go. In strategy two is basically we are using a sensors like camera, we use landmark and computer vision system. The thing is, In urban areas, you will have frequent intersections. You will have traffic lights. You might have some landmarks in terms of big buildings, something. We want to use them because we'll have it in our data set. So we have the landmark data set database, which has got the latitude and longitude of the landmarks. Using the camera and computer vision, we will detect if we can detect the landmark. So we retrieve the nearest landmark latron, and based on that, we correct the location. So I will show the result how we are correcting, and that corrected location is sent to the AV localization, and that is sent to the navigation system. So AV localization also update the means its location so that it can go for the next landmark. So we track from landmark to landmark. So this is our experimental setup. We have this car. It's not autonomous, but like we have our CPT-7700, which is a pretty accurate GPS with IMU, tactical radar IMU. We have this antenna, we have this camera, and we have the GIS OSM map we use for extracting the latron along the route. And for the experiment, we need to a little bit change in terms of like data set. We fed into the landmark detection time step because we are not using camera at that point, but I also show a live demonstration where we use the computer vision. But for the results I'm showing, we are assuming that we are already detecting the landmarks by computer vision. So this is the route we created. This is our famous stadium, and here this is inside our campus. So we created this route, and we extracted all the laterals along this route in every 10 centimeters. These are the points, landmarks. So what happened is I extracted all the intersections. When I was doing it automatically, there are like two misses. So I added that manually. Other than that, all of them were extracted using the ArcGIS. So if we look at the location error, you will see that we use LSTM and Kalman filter. And the mean error is 6.23 meters for LSTM, and for Kalman it's just 3.44. It's like almost 45% improvement. And 3.44 meters error is pretty good for any system which is not using GPS for correction. Here, if you look at the vertical bars, that's where the landmarks are. So if you just zoom in one, you can see that whenever that vehicle was here and landmark was detected, this yellow point is shifted to this point. So this is the correction happening. And whenever you see this vertical bar, so in every vertical bar, every landmark is corrected. So though it's trying to climb the error, we are trying to minimize it at each landmarks. So this is basically the output. So both of the navigation work, LSTM and Kalman filter, but Kalman filter worked pretty like fabulous than the LSTM. So we tried to use the Kalman filter for our demonstration. So we did it in uh, the US DOT headquarters. I guess Dr. Chaudhary was there, Dr. Bhavani was there. So you can see this one is the estimated that we are using Kalman filter, the yellowish one, and the green one is the ground truth. They are pretty much matching. And whenever there is you see this stop was detected, it is just there is a like jump, so it's correcting it. Right now there is no attack, so it's not detecting any attack so far. But at some point we will introduce the attack. So there will be a shift. So just look for it. And here you can see it's detecting all the stop signs. So here another correction happened. Now we are adding this spoof signal, that the red one. So at the same point time when it was introduced, we are detecting it. So after that, what happened? We stopped the GPS, and now you see the estimated location, which is coming from our landmark-based one, and Kalman filter is really matching with the ground truth. So though the spoofer is trying to show that I'm here, but I am really getting the actual location of my place. So using that, we can really navigate from one place to another when there is no GPS. Now the question is how long it can hold. So that's where we have to push the route bigger. But for this route, it worked pretty well for us. Okay, so I rushed a little bit to finish everything. So in conclusion, the thing is the autonomous vehicles are already deployed in the public roads, and they are heavily dependent on reliable navigation. The navigation stack is critical, and it has got vulnerable components. If we just do the static analysis, that cannot identify the all real operational risks, so we do the hybrid system where static and dynamic both analysis are used. Then integrated GNSS system vulnerabilities we could figure out, and we could do the pen testing for the GPS spoofing. And after doing the threat modeling, we also have a detection method using the particle filter. And if nothing works and we cannot use GPS, we have a method where we can use landmark for navigation for at least a limited period of time. So that's basically the whole talk about. And thank you for your attention. And I'll be happy to answer any question.
Thank
That
you,
was
Dr.
a
Dasgupta.
really good presentation, Dr.
Thank you, Dr.
Dasgupta.
Bhavani.
Yeah, I learned a lot.
Thank you, Dr. Bhavani. Appreciate it.
Thank you, Dr. Dasgupta. So now it's the question session. If anybody have a question, you can write it on the chat, or you can feel free to unmute yourself.
So I have a question. It was a very good talk. So
Thank you, Dr. Khan.
In your first set of work, you mentioned you do static analysis and do the dynamic analysis. Usually, my observation is dynamic analysis is very expensive. So I assume that you do the static analysis, and then on top of after the static analysis, you do dynamic analysis, right? For a few cases.
Yes, correct.
Okay.
So
and
the
then,
first thing is we get the CWEs and the lines from the static analyzer, and then we try the dynamic analyzer only on those functions.
Okay. And and then you also showed, I think, some cases it may not be reachable or something, right?
Correct. Yes.
Yeah. Okay, that's very impressive work. Thank you.
Thank you, Dr. Khan.
Sagar, I have a question. So,
Yeah.
so the GPS generated environment, so you're moving based on the landmark. So, have you tested like how long it can do it? Like, so some threshold that after this it will not work?
So, so based on our last experiment, and
Yeah.
I cannot talk about the length of the thing, but it went well for 15 minutes. So we didn't test more than that. We have to do it. Yeah, we have to figure out and when it breaks.
The extent, like
sometime it should break.
Yeah, what is the threshold when it will
Yes.
not work or something?
Yeah, definitely we have to do it.
Thank you. Thank you.
Okay. We have a question in the chat box from Mr. Richard Stewart. He said, did you jam the GPS signal, then restart with a spoof signal to test if the filter knows which of two signal is a spoof signal?
So, the first thing is how we define the attack was basically sending the spoof signal by wire. So what we did this time was mainly sending the spoof signal and see how the receiver reacts. But one of the Garmin case I was showing, it was basically first jamming and then introducing the spoofing. The reason was, so as it was under the shade and it was trying to, at some point it was trying to figure out whether it's if it's getting any signal or not, because whenever there's a continuous signal coming, so the receiver is locked onto those signals, right? That's satellites. So jamming is that's the logical thing to do first, so that all the locks are gone, and then you introduce it. But for our experiment, we were just sending the spoof signal and seeing. We didn't do any jamming. We were continuously sending the spoof signal.
Okay. He had another question as well. He said, did you test the filter dealing with multiple spoof GPS signals sent at once?
Okay, so the scenario, I was a little bit hurry. So the thing is, whenever there's a spoofing scenario, so there is a constellation of maybe, if I just think about the GPS, sometimes 8, 9 GPS satellites are there. The thing is, are you spoofing the whole constellation, or you are introducing some 2 or 3 new satellites or spoof satellites? For our case, what we did, we introduced the whole new constellation. So no correct or authentic signal was getting inside the GPS receiver. So it was the whole constellation was spoofed, the fake.
Okay. Does anybody else have a question?
Thank you, Dr. Nambi-san.
So
You're
it is.
welcome. I enjoyed the work and delighted to see the progress.
Thank you,
Thank you,
Shashi.
sir.
Thank you. Yeah, Shashi is a very good friend of mine. Yeah.
Thank you, Ronnie.
Any more question? Or it's almost 3.
Yes.
So if there is no more question, thank you, Dr. Dasgupta. It was a pleasure working with you, and you are our true scholar. So I'm looking forward to your next advancements. Thank you.
Thank you,
Thank
Dr.
you very
Chaudhary. Thank you,
much.
Dr.
Thank
Stewart.
Thank
you.
you. Thank you,
Bye.
everyone.
Thank
Thanks.
you all
all.
for joining. Wishing you all happy holiday and
Yeah.
see you all next year. I will share the video by this weekend. So for those who want to watch it again, it will be available on the Tracer
Yeah.
YouTube channel.
So, Jean-Michael, I just want to say one thing. I've got some ideas from what he said. Latifa and I did somewhat similar work long time ago. I want to check with Latifa, and then maybe if you have any questions, we will also contact Dr. Dasgupta. Thank you.
Yeah,
Yes, ma'am.
I'd
Thank
be
you.
happy. Thank you so much.
Thank you. Bye.
Bye.
Thank you, Dr. Dasgupta, again.
Thank you. See you.
See you.